pop-up blockers on your browser. Now, on to our webinar, The Challenges of AI on Power Distribution. Joining us today, our expert session, are our guests, John Berenbrook, Director of Product Management at Starline, a division of Legrand. Welcome, John. We're also here with Christopher McLean, Principal at Critical Facility Group. Thanks for being with us, Chris. Now, allow me to introduce today's topic. The global data center landscape is undergoing a seismic shift due to the rapid growth in artificial intelligence compute demands. This accelerating growth in AI workloads means profound changes in data center power requirements and infrastructure planning. As AI technologies advance, data centers' power demands and infrastructure requirements must swiftly evolve to accommodate increasing power densities, changing hardware configurations, and dynamic workloads. The aggressive growth in power density is challenging the entire IT energy industry, from utility services to standby power topology to the server cabinets themselves. Okay, data center facilities design criteria must now embrace new possibilities and approaches when it comes to the data centers that will soon and increasingly support AI workloads and their escalating demands. To find out more about the latest advances and practical ways to make data center power capabilities ready for the AI future, we begin with our main session of the day, presented by John and Chris and moderated by me. Again, if you want to ask any questions of our speakers at any time, please use the Q&A box that's on the right side of your screen. Okay, good to be with you, John and Chris. Let's start out getting into this very meaty topic. John, you can't turn on a computer or phone these days without hearing about AI and its impacts. Everyone is trying to understand how this affects them and their organizations as well. How quickly is AI changing the planning process around the power structure for future data centers?
Boy, it is insane how fast it's going, isn't it? I feel like, from a layperson, we just heard about ChatGPT a year, 18 months ago.
Right.
And now, everywhere you go, you open your laptop, every application, every web application, every search application, everywhere it's being integrated, right? And so, I thought it was interesting the other day, working through some of these slides, just some of the standard tools that we use every day. Search, even things like Adobe PDF. Why would there be AI in your PDF tool? Well, it can summarize it for you now. And so it's really, the applications are as limitless as our imaginations. And just like, it's almost like the internet before it, let's see where this technology can be used.
Sure, and underneath all of that activity, there's got to be some systems that are supporting it. So there's a wellspring of interest and demand, but that means a dramatic shift in the infrastructure use and demand as well. So what are the implications for data centers now that we see this really fast and intense shift in the market?
Well, I think the implications are that we better be ready, and we all better be preparing for these next stages. So, when you look at the market data, Gartner's saying 70% of people are exploring generative AI. IDC is saying software is going to be around an $800 billion industry by 2025. It feels like those numbers may even be low, to me. It feels like we're beyond that. Even smaller companies are, hey, how can we utilize this? So when you look at the implications for data centers, I think the answer is that it's all of the above as far as changes go. You have increase in power, you have more data centers, you have different types of data centers using AI. So that's where I think that we really are going and what's going to change.
Now, in the past, we've usually had quite a nice ramp period that we can adjust to some of the shifts in the market. What's different about this one? Past is not prologue necessary for understanding the impacts of AI on data center power density and other factors.
Um,
John, I have a little anecdote here. It takes
sure.
us, maybe two steps back, but I think it'll give some color to Dana. A number of years ago at an industry conference, the keynote speaker was talking about like social media, just in a generic way, and how you could be in like the APAC countries or the FLAP countries, and you could spin up your favorite social media, whatever it was, and how that was triggering power to be consumed in the United States by a data center. It was triggering the consumption of bandwidth on U.S. networks and communication systems. And John, I was thinking about sort of this slide topic and the transition from the previous slide where you were talking about sort of Adobe and how AI is integrated there. If you go on LinkedIn and you try to, do a post, it'll recommend, AI filling in your post and doing an auto post for you. You can go on ChatGPT and say, I want to post on LinkedIn about data center industry, show me news headlines and aggregate them for the last, 30 days. And it'll give you something to post. On LinkedIn, again, if you say, I'm going to post a job description for an electrical engineer, it'll write a job description for you. So it's already here. All the things that we're talking about, they're being cut into the data centers already. And there's small companies that you didn't hear about 2-3 years ago that are leading the charge. You always hear in the data center industry, we defer to, this search engine, this software company, this social media company. It's all these big, huge companies everybody's heard about. In AI, it's companies that, didn't exist in sort of the public acknowledgement sense just months ago. But the technology's here already. It's implemented, and now we're reacting to it and trying to find ways to modify and augment facilities to cut it in to fuel that growth, to make sure that that technology is available immediately, since the technology's it's already available. Sorry to cut you off, please.
No, thank you. And yeah, John, I'm just trying to get a sense that the way that we went about planning for power consumption in data centers in the past, is that outdated from this rapid adjustment that we need to make for AI, or can we use that as a template?
Boy, that's the $1,000 million question, whatever you want to call it, right? I mean, so I think the market is dynamic right now, and we're seeing, I'll call it, I want to call it standard AI deployments, but using standard technologies and deployments we have, and maybe it's just out of necessity that's where we are right now. But we envision over the next year, 18 months, and different. So, Chris, I know that we talked about this slide a lot, but will the cloud kill the data center? Will AI kill the data center?
Yeah, that's fair. Thinking about this as a design engineer for so many years, every major data center conference, somebody spoke on cloud killing the data center. And I think they got it wrong. Cloud was just another data center, or, cloud-based services, software as a service. They were applications in a data center. And, what we had was just fueled growth to bring us to, an echelon that nobody predicted. And AI is not different in that it's gonna fuel us to a level that nobody had predicted, 3 years ago, 5 years ago. So this slide, coincidentally, this slide is an aggregation of data that I put together for Starline for their annual symposium, for Legrand's annual data center symposium. And what's in orange were 2020 values for data center consumption, available by major data center real estate developers or data center tenant placement agency, multi-tenant data centers. Doesn't really consider the hyperscalers and what how secretive they are about their deployments. But in just 3 years, from 2020 to approximately 2023, we see this seismic growth in these other markets. And that's where like the orange yields to the blue. There were markets that just popped up out of nowhere because they had power, because they had land that was affordable, because they had access to network. And so cloud didn't kill the data center at all. It drove us to new heights. AI is going to drive us to much greater heights and faster. There's no limit to where it is now. What I was saying in our sort of pre-meetings, John, it was AI is instantly everywhere all at once. every RFP that we're seeing on the design side is, how do I augment some percent of this facility to bring AI into it? In some cases, like your most immediate point that you made here in this slide was, we're trying to make use of existing designs. Design's expensive, and the end users deploying designs, they have trusted engineers and architects that they've been working with for years. They have a lot of investment in really mature go-to-market strategies, so they want to use them. But the density and the demand is so different now that in one design, we had a design that we've deployed some like 8 times for one particular end user. They did a wholesale AI cut in, and we were only able to populate 11% of the floor plate while using 100% of the mechanical and electrical commodities that were there for that particular thing. So now we're retooling their design to try to say, well, what if we were going to do a hybrid again? Could we do it better? What if we were going to do just a standalone AI? And so we're having to go back, left in the schedule to say, let's put our thinking caps back on and rejigger how we would approach the market with what we know now. And I think you're going to see that in a lot of these markets. They're going to, they're going to come and say, hey, data center community, pay attention to me. We have a lot of power. Maybe we have a lot of green power. We have a lot of hydropower. We have, something really specific that's attractive. Certainly in Pennsylvania, we just heard about a nuclear power deal with one of the big hyperscalers. And so anywhere where there's power now, you're starting to see these AI deployments want to deploy there just because their technology is so hot. They want to get it in our hands as consumers of this technology. So I think the message on this slide is, it's a little tongue-in-cheek. AI obviously isn't going to kill the data center in any way that the cloud killed the data center. We're going to fuel growth to new heights, and we're going to be in maybe undiscovered territory. We have Nashville way on the right-hand side of this particular chart that's almost 2 years old. But I'm working in different markets right now that weren't on the data center map of years past. It's certainly light years beyond the NFL cities map that we used to go by 10 years ago into secondary and tertiary markets. Now we're just into lands unknown, places where there's industry, business, access to a substation, access to power. And I would see this chart doubling in the next 2 to 3 years in terms of quantity of cities with some level of data center, because the densities are so high, it puts you on this map with one building. And that's just remarkable.
So we should, like with cloud, expect more of all of the above when it comes to demand for compute and resources, but we don't want energy and power and heat to be the mitigating factor, what gates us from getting to the growth that we want. And it's going to be a very competitive environment, so everyone's going to be looking for that data center. So where do we go next with this, John? How do we understand what's going to be required, not only where you place your facility for general power availability, but to make that power work in appropriate and economic fashion to satisfy these high compute demands?
Yeah, I mean, so Chris mentioned it a little bit on the previous slide, but when you talk about power, it ultimately goes down to the rack and the power design. So, we're projecting a 50% increase in the power footprint by next year, which is wild. When we think about the history of where we were, it's really quite astounding. 10 years ago, we're really deploying 3 kilowatts per rack, 5 kilowatts per rack. It wasn't a significant, significant power consumption, of course, yes, by any stretch of the imagination. But for the scale that we're at, we're talking, millionaires versus billionaires now, basically. The scale is so different. So, when we started 120 volts, 208, 120 single phase, it's not much different than plugging into your outlet of your house, for example. And now we are right, the standard of design is 400 volts. And we see facilities at 480 volts. So what does that mean from a power supply, from a safety standpoint, and all of that, right? So, we started to see, with the advent of the cloud and the hyperscalers, we started to see the power densities climbing. And and, 5% or 20%, 5 kilowatts might be 20% power increase on a rack. And that seems significant. And we're moving to, say, three-phase type outlets, for the rack to supply power to the rack. We're still at three-phase outlets, but now it's much higher. The amperage is much higher. So the kilowatts we're delivering is much higher. And now we're delivering more, three outlets, 4 outlets, 6 outlets. So, where we're going is a little bit unknown, but where we've been, I think, is a good indicator of how we were going to approach these problems.
Chris,
yeah,
what
John,
can you
let me
offer?
add to. Yeah, sorry, Dana, to cut you off. Yeah, I was going to add some color to that. Just, as a design engineer and, a former data center operator, the most common request from a, power density standpoint, from a, electrical receptacle standpoint, was an L630 for many years, 3 to 8 years probably. That went from 20% of your environment to 50 to 80 to 100%, and then it started backing down again. And what you're talking about, a 5 kW rack, effectively, just like you said, John. And the average utilization of the 5 kW rack was typically 3.6 kW. And the industry kept telling us a higher density is coming. Year over year, the big data center conferences were higher densities coming. In 2011, I reviewed research papers for patents from grad students at Brown University and grad students at MIT, for heat exchangers at the rack. Really just server level heat exchange in the chassis of the cabinet itself. They just want to take the heat rejection right inside the cabinet and transfer it to some medium, because the density was going up. That, 10 years ago we were talking about it, but it didn't happen. I mean, did it go up? It did. And like you said, it went from 5 to 5.5, and that 10% growth was massive. On paper you say, well, it went up half a kW every 8 square feet in the data center. It didn't really feel like much, but when you look at 5 going to 5.5 or 5 going to 6, it's a 10 to 16% increase, and all of a sudden that sounds pretty massive. As the network appliances changed, we started seeing the environments shift, where the L630 yielded to like L2120s, again 5 kW, but now 3-phase power, like you said. And we started proliferating entire rooms with that, and then it jumped. It was now 3-phase 30, 3-phase 40, 3-phase 50 and 60, but only 7 to 10% of your environment. The power density did come, but not at scale. And we were starting to see sort of availability zones emerge in data centers, where we would say, well, we have 100 cabinets, and 5 years ago, 100 of them were 5 kW. Well, now 20 of them are something different, and they're spread out. Or, one row is this, and then, 2 cabinets in every other row are that other thing. And we were spreading load out for heat density because we wanted to sort of absorb that heat rejection into the ballroom of the room. But the moral of the story is that, L630, L2120, 5 kW rack yielded to something a little bit bigger. It was maybe 12 kW, 14 kW. But again, only say 7 to 15% of the environment. And now we're seeing that go away, and we're seeing 30 kW cabinets for 100% of the environment. The shift was overnight with regard to AI deployments. It made data center designs of the past nearly completely unusable. You couldn't just add 5 times more UPS capacity and generator capacity on your lot without a great deal more land, or without a great deal more risk and structure trying to stack these things. But the confluence of events causes your white space to shrink dramatically. So you've yielded space in the infrastructure that you're building from data center white space, which from a co-location and multi-tenant data center environment was always, that was the holy grail, like leasable space. How much space can I lease? Well, now you're building rooms just for tiny footprints, but 3-4 times the mechanical electrical space to fuel the growth and power those devices and reject the heat from those devices. And we're getting into really uncharted territory. There's only a few companies on Earth that are doing this. Like you were saying, John, the way that we're dealing with it is with higher voltages. Unfortunately, electrical just isn't the most efficient game in town. When I took the professional engineer exam in 2011, I bought a book on eBay for like $3 that was from the 1950s that had unbelievable detail on how to parallel transformers, impedance matching, things like that. And, guess what? It's still absolutely relevant today in the 2020s. The sort of most influential thing we've had in the data center market on the power side was decoupling UPSs in the sake of efficiency. But, holistically, all the same parts exist. And when you put them all back together, it's still the same inefficient thing it was 15 years ago. Dana, as a former three-phase UPS person, you could attest to this being true. But what is beneficial, what does move the needle, is raising the voltages. If you raise the voltages, the ampacity comes down, and you can deliver more power to a rack with smaller conductors, less copper in theory. But you sort of shift into this uncharted territory whereby, people at their home have track lighting, and they're used to, turning off a light switch and twisting into that, and then turning the light switch on and being able to deploy lighting in any way they want inside of a room along that track. And they're comfortable with that. In 2007, when I specified my first data center with Starline busway, you're trying to get the IT folks to adapt towards twist locking into 60 and 100 amp busway was a very unique conversation. I remember bringing in sections of bus and having them twist into it with people just, trying to stabilize and hold it so they could practice and getting used to the action and getting used to working overhead with these things that, it's not a light, it's something a little bit different. It was a little intimidating. And now, as you're saying, John, that track busway is not 60 amps anymore. It's 800 amps. And the voltage isn't 120, it's 415 or 480. And now we're asking people to do something that might feel a little bit different again, but in the name of efficiency, in the name of density, we're at a big inflection point in the market where people are adapting to these new norms and trying to get comfortable with something that you don't see in your house. You don't see it in a commercial office. You only see this in the data center, really. And they're trying to get comfortable with the technology that's sort of evolving around them to keep pace with the software. Like, all the hardware is changing, not just the computer hardware, but all the electrical distribution apparatus, all the mechanical cooling and heat rejection apparatus. All of these things are changing to deal with the density, and we're all getting used to it real time, trying to adapt, the way that you're talking about the design criteria changing. We're trying to adapt to these sort of new norms and, new and different and bigger technology to satisfy, handling these higher densities, higher electrical loads, higher heat rejecting loads.
So before we get further into the response to these challenges, let's get some more details on the new demands on the data center and how AI is unique in that, different from the past. So, John, going back to your flow on your slides, what is the idea that we need to get through to people to understand why this is different and why time is really not our friend in making these transitions?
Yeah, and I'll tell you, it's interesting. So, and I'm seeing some comments and some questions about hyperscalers have been at 10 to 15 kW per rack. So, but interestingly enough, Chris and I were talking. So we've been working on rounding out this presentation for, I don't know, 3 weeks, 4 weeks, and in the time, the difference in requests that I've seen has already changed. So it's already, the speed is already here. In fact, just 10 minutes before we started the session, I had a request to see how we can power 100 kW racks, right? So it's really, and it really doesn't even stop there necessarily. So when you look at that in terms of demand, this was a report from McKinsey in 23, so a year ago, a little bit more than a year ago. And I bet if we did the same report again, this would look more like a hockey stick than the way it does today. So it's really imperative that we wrap our heads around this and we proceed in a safe way and a reasoned way in designing our power distribution systems to accommodate these incredible loads.
Now, Chris, you mentioned a moment ago that the old way is just not going to work, that we need to have a sea change here. What sort of design considerations do we need to consider? How do we get out in front of this, knowing that the way we did it in the past is not going to scale?
Yeah, actually, can we stay on the previous slide with the vertical chart? Um, so just anecdotally, I've been I've been working in and around data centers since 1999, and professionally started designing data centers in 2007. Um, Working with some hyperscalers and big multi-tenant data center environments up into 2022. I can say that I worked on somewhere around 5 gigawatts of data center, and I saw something like 3 gigawatts of data center commissioned, and I touched some 300 environments. And I stopped tracking it at that point. It used to be sort of a badge of honor on a spreadsheet and looking at all these things, that these awesome places that I had been in, projects that we had worked on as big teams. In the last year and a half, we're working on over 12 gigawatts of data center. And in the next year, that's the RFPs that I'm seeing, they exceed that 12 gigawatts of the past year and a half already. And so in the last year and a half, I've literally worked on the design, or so the permitting or the load letters and the interfacing with the utility companies, and 4 times more power capacity, ultimate power capacity, than I did in my entire career to date prior to that. Working with one end user, they say that there's a new entity to the U.S. market coming that has a 5-year, 15 gigawatt data center consumption plan. We're talking about companies that, like I said earlier, that we didn't even hear about a year and 2 years ago. These are new players. These are not the search engine companies. They're not, I see in the chat here, people are talking about what some, search engine company or somebody did for the last 15 years. And just respectfully to the Q&A, you're talking about 5 companies on Earth relative to the quantity of data centers on Earth. 12, 15 years ago, there were exactly 10 million square foot data center sites on Earth. Last year, there were over 650. And we're talking about, the Q&A, like I said, with the sort of the power consumption stuff that's in there. You're talking about 5 to 8 end users. We're talking about the other several thousand. But in terms of AI, we're talking about a new group of players that didn't exist, doing something at a completely different scale. Just add some color. So we could shift to the next slide.
Great points.
Oh, thanks, John. This is I'm sure some folks would challenge this, but I sort of got vilified many years ago. In 2011, I went to a data center conference, and just on the heels of coming out of a bad situation with a client who wanted to design an X number of megawatt data center, they didn't bring the load. That's always the case here. It's like, we want this most efficient data center. We want to do this demand thing that you've never seen before. We want to be at this power density you've never done before. At the end of the day, the humans are the biggest problem. I mean, we're doing this webinar, and any one of you, I challenge you, go look at the resource monitor on whatever desktop computer, laptop computer you're using to view this, and you're probably pegging the needle to the right at 1% of your hardware consumption. And that's sort of the limitation of the data centers too. We're limited by the humans. The technology is getting more sophisticated. We're doing more compute per kW, exponentially in the last 15 years. I think as an average, we were increasing some 6x per year for a number of years. And so I did this comparison, on the left and the right, 5 years even before this chart existed. And just talking about resources inside IT hardware, how inefficient the power supplies were relative to the cost of the power supply. And, if you were buying 10,000 commercially available servers, versus building your own, you might save, I don't know, $15 per power supply to get the silver or gold instead of the platinum efficiency version. And, that would change your efficiency by, 7 to 20%. And if your power supply was 20% of the load of your server, and you have 1,000 or 10,000 of these things, that's really significant amount of inefficiency that you're accepting for very little dollar investment. And so at this point in time, I was saying that, the MEP engineers aren't the enemy here. We're given, really incomplete data when we're asked to design a facility. We don't get the data that's on this slide. We don't get how much RAM you're deploying, what software you're using, how the software utilizes the hardware. We want a 15 kW box, and we're going to use the power. but you have to actually bring the load to get these systems to operate efficiently. And so the interesting thing about the power density slide is AI is, again, very different. And this isn't going to become a CPU versus GPU conversation. This is just the scale of the things that we're designing to. The 5 kW racks of the past are gone. And these are the different components, in 2020 with that ResearchGate, these are the components inside of, the server or the Apple, our IT appliance that are consuming energy. And, where are we going with this? We could jump slides here. This is a real case now. We're talking about 60 kW racks. And we're talking about something that's 4 rack units, 1.75 inches times 4. And each one of those having 3 2,000 watt kW power supplies. So you're talking about 6 kW every 4 rack units, and 10 servers per rack yields 60 kW rack. In the R&D sort of realm of things, critical facility group, we're deploying right now 34 kW racks. We're designing 80 kW racks in another facility. We're looking at cut-ins of 100, 150, and 200 kW racks over the next year and a half. Says the 200 kW rack client, the heat rejecting system to do what we want to do on the IT side doesn't exist yet. It hasn't been theorized yet. Certainly people could argue that, with immersion cooling and chip level cooling, there's some validity to that, to getting to the 200 kW. Forced physics is doing something with 200 kW, but in a much wider floor plate. But if you're talking about, a 2-foot or 30-inch wide cabinet and doing 200 kW in that sort of 8 square feet, 10 square feet, nobody's cooling 200 kW yet. But what we're getting for RFPs right now are trending from 1,600 watts per U to 3,200 watts per U. And what John was talking about earlier in the call that he received before this started, we're not talking about 30 amp 3-phase per rack. We're talking about multiple 100 amp 3-phase per rack now. And how do you approach, from a power standpoint, we could throw a lot more copper and a lot more busway at these things and get the blinky lights to blink. But how do you deal with the heat? How do you deal with the pitch and the yaw of the room? How do you supply air to the face of this thing at all of the different levels of, air column that the servers are trying to consume from? How do you bring chilled water to these devices? What's the capture of chilled water at all of these devices? Like I said earlier, the designs of the past that have been matured for years, they just don't apply anymore because the technology is so different. And it's so different at every 1.75 inches. It's not different in like 20% of the environment every one. It's every 1.75 inches is so wholly different than 5 years ago that everything that we think about when we go to design and construct one of these environments, everything else has to be different and elastic to be able to meet that demand too.
So John, it sounds like we're going to be hitting a limiting factor via the power and heat considerations for growing these markets as the market seems to want to grow. Is that right? Are we going to be hitting up against some sort of a limiting factor, or are there steps that we can take now to help ameliorate that?
Yeah, I mean, I think that's a great question, and depending on how far we go is probably the answer to that question, really. But right now we see on the distribution side, when you look at 3 2,000 watt power supplies per GPU, right? What does that mean for actual deployment? So what we find is that every deployment's a little bit different. Some of them are retrofits. And so how do you fit, let's just say, 3 600 amp busways into an aisle? And then is that redundant or isn't it? Or are you just supplying that power at 400 volts, right? So those are the questions that we can help with. And when you look at the density of it, us supplying that power is really the challenge, I'll say. How is it overhead? Is it under the floor? Is it, where is it? So, and Chris, you were talking about heat, certainly heat rejection and the different ways we're capturing it. I mean, is there more to say on this slide, do you think?
Yeah, absolutely. It's the heat rejection of today, looks like something more of a science fiction. I can see in the comments somebody asks about air cooling these higher density racks. Absolutely possible to do it with air. To be honest with you, have done 60 kW racks with air. The the change here is on the construction side. Folks think about, these are $500 square foot, $1,000 square foot facilities, and 60 to 80% of the cost is typically electrical. And now that's not changing. That's still the whole total cost is going up, but you're still say 60% or maybe a little bit less of that total cost is electrical. And now you're seeing mechanical costs go way up, where we were bringing perimeter cooling and trying to move air or using plenums in direct outside air systems that were filtered, and trying to dump CFM and control pressure across servers and use hot aisle containment strategies, trying to eke all the efficiencies out of an airside delivery system that you can, using really, really wide approach aisles, columnizing your heat rejection to get it into a different air, to stratify into a different elevation of the facility sooner, faster, and reject it to atmosphere sooner, faster. There are a lot of things that were happening. But now where you're bringing chilled water directly to the rack, which is not totally different than in-row cooling units, having chilled water adjacent to the rack. I mean, certainly there's companies that have been doing in-row cooling, and Ratal has been doing water to the rack with sidecar in-row cooling for 15 years probably now. But now when you bring it directly into the rack to something like a CDU, sort of something more akin to what you see on the left side of the slide, you have a lot more copper or some sort of piping system under the floor or overhead that's going to every single rack position. So your mechanical system costs are going way up. If it's water, there's different applications for vacuum pumps. If you had a leak, it pulls into the CDU, or you're putting some sort of bathtub around under the floor, or you're putting some sort of leak capture systems and leak detection systems above the rack. So your mechanical costs are starting to go up because you're trying to capture your heat at the source. The thing that we're finding with these, the chip level cooling, is that they're being advertised at 100% capture. And when you, sort of peel back the layers of the onion, they're more like 90%. When you peel back a little bit more, they're more like 70%. And so we're doing something that's new and different, but at the same time, you still have to do perimeter cooling or some sort of other supplemental cooling, because number one, you still have network components that aren't going to get the chip level cooling. So you're still going to have latent heat that goes into the room that you still have to deal with from a design and construction and operation standpoint. And then you have this whole other system that's really costly that introduces a lot more appliances to the building to capture heat at the server chassis, at the chipset, just closer to where the heat's being rejected. And that's in like the sort of the direct chip level cooling or the direct server level cooling.
So Chris, I think,
yes, sir.
Sorry to interrupt, but one of the interesting things I think we're still figuring out is on the power side, when you're powering CDUs or in-row cooling, what does that look like? Does that come from your critical load, and how do you monitor that, and how do you deal with maybe the consequences of introducing cooling loads into your IT loads? What do you think about that?
It's a great question, and I'm working through it on 3 projects right now, where you're either going to have to bring secondary PDUs or receptacles into your cabinet to pick up the CDUs, or you're plugging into your critical power PDUs and you're putting those pumps directly onto the critical bus the way that you described. And the interesting thing is that it shifts your PUE. It shifts some pump load and some pump energy from the mechanical side of the system to the critical side of the system, which depending on the efficiency of the system, it could be good from a energy standpoint. But then if you shift hundreds or thousands of pumps to your UPS, what does that really do to your UPS reaction and the sort of the coup de lit when you block load a UPS in a critical power event? So we're working through that in a number of places right now. And I think that the adoption is, it's okay to have the pumps on the UPS from the end user standpoint. They're not particularly big power draws, and we're not seeing particularly large harmonics or anything that's impacting the UPS's normal range of operation. But it's certainly something that is I'll say atypical. I mean, definitely there are applications for putting, pumps and drives and different things on UPS to survive a critical power event and, loss of utility and, transitioning over to generator. We look at that on basically every project, no matter what the density is. But this is a pretty overt thing where you have an HVAC appliance now living inside your cabinet and you have to think about how you're going to power it. And I would say so far everybody is elected to just put it on the UPS because it's easy. But we're having a lot more conversations about, well, what if you could get a little bit more capacity out of your AI? And how much do you lease that AI for? And how much would be what's the simple payback in terms of the return of investment to just put in thousands of additional electrical outlets to shift that load where it traditionally lives? So definitely a lot of things. I'm an electrical engineer, and the mechanical people have been having so much fun in data centers for 15 years. It really makes me angry. And here we go again. They're going to have so much more fun, and they're going to get to impact us a little bit too. So they have extra fun doing this efficient thing, and they get to make electrical a little more inefficient.
Sure.
Just get to.
So what I'd say is to kind of say that, from the electrical side, things that we've seen and what we've done to help people kind of suss out the PUE side of it is power monitoring really helps. And we have harmonic monitorings, we can put in our PDUs, our rack PDUs. And so there's a lot of ways that we can help pick those data points and make sure they're available for the DSIMs and the BMSs that are driving those decisions.
So given that we saw that hockey stick earlier in the demand or expected demand and the complexity of dealing with the power and heating issues that we've just described, it sounds as if so many more organizations and a handful of hyperscalers are going to be trying to do this all at once. Do we have supply chain issues, or are the bits and bytes going to be accommodated by the mechanical and the electrical, or are we not sure yet? How does the supply chain issue around making all of this happen fairly quickly and everywhere actually shake out?
Well, yeah, I mean, I'll tell you that if you've been in this industry on the manufacturer side, there have been supply chain challenges due to the growth year over year, regardless. So in some ways, we're well positioned to continue that same trajectory. Anybody that's been in the industry, you kind of live with this baseline level of stress and anxiety that maybe other industries don't have. As you're trying to make sure you fulfill orders and your designs are the correct for that moment in time. And so we are no different, right? And we're dealing with that. But we have been on the forefront of building out factories and localizing our supply chains, which really has made a difference in how we're able to respond to the different regions. So when you look at AI deployment, I think there's really, a 1, 2, 3 step process. And Chris, you might disagree with me on this, but I think we see the majority of requests coming from the US and North American market, right? And so we're well positioned to support from a supply chain standpoint there. And then we're seeing APAC is maybe 6 months behind where the US is, 6 to 8 months behind. Then you have Europe, which might be 12 to 18 months behind where the US is. So it's kind of rolling through. And so what we're finding out in the US market from a power deployment standpoint, changing. So I'll go back to the receptacles again. So from an L630, now a standard AI deployment is a 3-phase 60 amp, 400 volt type receptacle. So, and there might be 2 or 3 of those per cabinet. So when we talk about what Starline does as an electrical equipment manufacturer, you really have, how do we work with our manufacturers to switch over from 3-phase 30 amps to 3-phase 60 amps to 3-phase 80 amps to 3-phase 100 amps? And how do we know, we have to make sure that we have line of sight with all of that and be in great communication, not only with our customers, which we love to do, as well as, our tier 2, tier 3 suppliers. And that's really the challenge. And then to do it in a global manner is, certainly makes it more complicated.
Chris, given these very complex variables that we're juggling and trying to align, wait and see doesn't strike me as a very good approach to your planning around your facilities your data center design and layout, the location for these, taking into consideration sustainability and costs. Should people be rushing to try to solve these problems? Why is the timing of this such an important issue?
Yeah, I would say that the majority of the environments that we're designing, I like to use the terms elastic and flexible in that we're designing an environment that can be reused at a lower or different density. It's a little bit difficult to scale up without knowing what the upscale is. If you go from 30 to 60 to 80 to 100, I mean, just like John said, you're trying to put multiple pieces of busway over a rack that already has multiple levels of cable tray for, copper and fiber distribution. You just run out of space linearly inside the rack. And then certainly with the hot aisles, you're not wanting to have major power distribution in an environment that's going to get that hot. So we just start to get to these points where there's just only so much real estate to put things. But with the chilled water applications and the water to the rack and having to have something else like a supplemental perimeter cooling to handle latent heat load in the room, we're building facilities with secondary taps or the ability to put reducing fittings on. And if you were to say, all right, well, AI, we had to spend all this money on these CDUs and now we're not going to use them anymore. Or we're going to use them at a different capacity, or we're going to take out every other cabinet and put in in-row cooling units. We're trying to create environments that can be a little bit more elastic. So you mentioned sustainability. Somebody once told me the most sustainable building is the one that you reuse. And so in thinking about that, we want to make buildings that can survive the IT life cycle. A lot of data center RFPs, they talk about a 10-year building. If your IT life cycle is 3 years, for some it's much faster and for others it's not nearly that fast. But if you think about 3 years, with the way that sort of compute per kW and power density have changed historically, if you're in a 3-year cycle, by the time you get to that third life cycle change of IT, if your power consumption has increased and your heat rejection has thus also increased, you're going to be at the elastic limits of that building. And you have to start building the next facility with modern RFP requirements to take that next IT deployment, because it probably won't work depending on how much of the infrastructure has to be modified to receive the new technology. And so we like to think about that. The most sustainable building is the one that you reuse. And I forget who to attribute that to, but I'm not the arbiter of that knowledge.
We're going to have to go
so
to
it is important.
Shortly, but John, I wanted to get your response to, if I could distill a little bit of what Chris said, if you're going to rush to anything, it's rush to be future-proof. It's not contradictory, I suppose, to try to get that flexibility sooner than later. What can people do in summation to start to be on the path to be flexible and to accommodate these incredible demands, but at the same time, do it in a way that's not going to always be 10 years from now?
Yeah, I mean, so if you look at busway, for example, and kind of building on what Chris said, busway is a reusable product, and it is it is voltage agnostic up to say it's a low voltage standard up to 600 volts. So if you're at a 208 voltage now, you can easily reuse the busway at 400, 480 volts to start getting your power to where it needs to be. Of course, the upstream infrastructure has to be right. The plug-in units, the tap-off units, they can all be swapped out for the particular load and application. And so that all leads to a kind of a sustainable reuse type of life. And even beyond that, on the initial purchase of the products, you should look for somebody who's going to be giving you the embodied carbon already. So many of the major hyperscalers are requiring that as a feature of their RFPs, right? So what is your embodied carbon? If you don't understand your embodied carbon in your product, then that's an issue for them. And the last thing I'll say on sustainability, which is really, AI. So we talk about AI taking power down, and that's certainly the case. But AI can also help, right? And so building digital twins. There's a lot of companies that are implementing AI on the DSIM scale. So how and when do I ramp up that CDU? If I know what my power is and I'm monitoring my power appropriately and I'm monitoring my environment appropriately, how can we make that better? So that's what I would say. And flexibility, and sustainability. I think that's where we should leave it.
All right. Well, before we begin today's Q&A session, please direct your attention to our online event survey. It's available on the bottom of your presentation window. Thank you in advance for filling out the feedback form. And now on to our Q&A portion of today's event. As a reminder, to participate, simply type in your question to the text box located to the right of your presentation window, or click on the Q&A icon at the bottom of your screen. If we're not able to answer your questions today during the webinar, we'll be sure to share them with our speakers and they can reply to you directly. All right, let's tee up some questions. We've had some nice interaction from our audience. People have been asking about, demand issues and electricity. But let me get to one here. It's about the difference in design for training versus inference model data centers. Who wants to take that one?
Yeah, I can start, and Chris, you can jump in. So, when we talk about AI in this application, I think most of us are knowingly or unknowingly talk about training. So training large language models, training, whatever it is. When you're clicking on "Am I a human?" you're training a bot somewhere that knows what the sidewalks are or where the crosswalks are, right? So those are training algorithms and training models. What we're seeing on my initial slide for race to implement AI, those are based off of the inference model. So how do we deploy those training models, and is the design different? So I think the answer is potentially yes. So training models may or may not care in all cases. If let's just call it, the standard has always been 2n+1 or some level of redundancy to get to certain uptime requirements. And I'm not 100% certain that that's going to be the case moving forward for, say, training models. But now an inference model where we're using it, where the consumer, you're consuming that AI application, you're probably still going to want some level of redundancy. Maybe it's 5 to make 4 on the UPS structure instead of 2n+1. So you have different ways to kind of manage that design infrastructure depending on the application and how it's being deployed.
All right, here's another question on design considerations for uptime. You mentioned uptime just a moment ago. Is design for 5 nines uptime still necessary, or has that changed given these new types of loads?
Yeah, like I said, depending on the application, but maybe Chris, you can jump in on that. What are you seeing?
No, you're exactly right. I mean, the folks that are leasing time on the servers, they don't want any interruption because that's could be an SLA violation. So they're wanting that. But the folks that own the applications themselves, I'm seeing them relax their redundancy requirements. And there was some other Q&A on this also, but I've seen UPS topology for network applications, access to the database. I've seen those go, more towards the banking standards of 15 and 20 years ago to like a real true tier 4 network. But your network and access to the database might be 20% of your environment. And to one of John's earlier points, you might have 3 busways with a swing leg over rack. So instead of having a true 2N topology, you might have sort of an N+1 topology. I've seen a lot of, sort of trend more towards tier 2 on the sort of owner-owned and deployed AI versus, the folks that are leasing out their space. The folks that are building to lease, it's really not different in terms of the 5 nines and the tier 3 sort of minimums, Uptime Institute and ANSI TIA 942B standards. But definitely on the stuff that's owned by the big hyperscalers, I've seen relaxed requirements for other than the network.
All right, we have a question from the audience about location of data centers, that AI needs a database to pull data from to run through the algorithms. And the question is, where do these data sources originate, and how is that a factor in the design and location of facilities?
So in some cases, I have to be careful in the sort of proprietary nature of some of these comments, but I've definitely seen a trend towards fiber to appliance in AI in a way that I haven't seen in a commercial data center. So you might have a network switch at the top of a rack and have copper to the switch and then have fiber, out. I'm seeing 2 to 6, multi-mode fiber to every single chassis. It could be a 4U chassis and, have 10 of those per rack and having 2 to 6 fiber to every single device, and then that aggregate all the way back to your databases. And real focus on things like InfiniBand to try to increase speed and have your network appliances really in close proximity. Speed is definitely an important thing. And I'm a power to get blinky lights person, so I'm a little over my skis in this conversation, but definitely have seen a lot more fiber, relaxed overhead cable tray requirements because copper's heavy and fiber's not, but the proliferation of tons and tons of fiber also takes space. It's not particularly heavy, but we're seeing increased demand whereby you used to have like fiber guide hanging off the side on a J hook of a cable tray for copper. Now we're seeing whole troughs, 2 foot wide just for fiber delivery to try to get, reduced latency to those other applications. Geographically, I'm not sure, if you're talking about outside of the facility, certainly that also exists, and we're still seeing most folks want 3 service providers and sort of triangulate the building to on-ramp to other, cloud-based services or, other of their own facilities.
All right, we have time for one more, and we did get a couple of queries on sustainability over again. So I want to give one more shot to you, John, about sustainability considerations. They go hand in hand with the economics. Any last thoughts to surmise how to consider sustainability as an important design ingredient when looking forward to the AI power solution?
Yeah, I mean, so I will say, I'm going to talk about it in terms of regulations. And I think that, I represent a manufacturer, and from our perspective, we are being pushed extremely hard and want to actually lead that charge. So Legrand is an incredible company from a sustainable aspect. It is part of our core of everything that we do. And, but it also goes hand in hand with where the markets are going to push for that, right? So I mentioned embodied carbon. Understanding that is the first, it's kind of like, miles per gallon. If you're not understanding what your gas mileage is, how can you improve upon it? So you have to start somewhere with sustainability, and you have to understand it. But the regulations that are starting in Europe are going to push across the world like they typically always do, right? And they'll be adopted. But so it's things like we mentioned PUE, and is the cooling infrastructure on the IT loads, and how can that affect PUE? Well, some of the early standards in Europe that we think are going to be coming might be the fact that even things like server fans are not part of the PUE. Like, that's really a cooling device, right? So how do you separate that out, and how do you start to measure these things so that we can make real progress on the things that matter? I think that's really the takeaway on sustainability. Nobody knows how we're going to pull down this much power and how we're going to do it. I'm sure, I'm not a utility guy, but I'm sure nuclear, renewables, all that stuff is going to be part of the answer at some point. But really, I think measurement and understanding is going to be the key.
Certainly a lot to consider along these very complex topics, and I'm sure we'll be speaking about them a lot more in the future. I want to thank everyone with that, because we've reached the end of our time for today's IT Pro Today webinar, The Challenges of AI on Power Distribution, sponsored by Starline and broadcast by Informa. Thank you to both of our guests, John Behrenbruch and Chris McLean. IT Pro Today appreciates your time and expertise on these topics. Lastly, thank you one and all to our audience. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation and some other resources to view on demand. Please feel free to invite your colleagues and peers who may not have been available to watch today's event. They can also access the whole thing and these resources on demand. This webinar is copyrighted 2024 by Informa. The presentation materials are owned by or copyrighted by IT Pro Today and Starline, and the individual speakers are solely responsible for their content and opinions. I'm Dana Gardner, Principal Analyst at Interarbor Solutions. Thank you so much again for joining us. This ends our event today.